Hello, everyone. Welcome back to another episode of Adventures in Machine Learning. I'm one of your hosts, Michael Burke, and I'm joined by my co-host,
Ben Wilson.
And before we get started, I sort of want to explain a little bit of the origin story of this episode. I used to work in A/B testing at a company called Tubi, and that's Fox's streaming service, so sort of think Hulu and Netflix. And the org had really good A/B testing, surprisingly advanced for the organization maturity. And so a lot of my job was staying on the cutting edge, reading company blogs or white papers. And so one rainy afternoon, as one does, I was flipping through recent publications, and I stumbled upon some research by Micheal McCourt, who is our guest today. And I was very grateful to hear that he had 90 minutes free on one Friday, and he's willing to speak with us today. So I'm really excited about what we're going to be covering. And the reason is Mike is head of engineering at SigOpt, which is a company that was acquired by Intel in 2020. He has over 19 publications, some of which we'll hopefully get into today, 4 patents. And yeah, so Mike, let's jump right in. And can you explain a bit more about what SigOpt actually does?
Absolutely. Thank you both for inviting me here today. It's my pleasure. Always happy to talk about SigOpt, talk about stuff that's exciting, and making sure that we get the cool topics to the forefront of the conversation. SigOpt is a company that was started in 2014, very, very late 2014, in order to provide what at the time we sort of just phrased as black box optimization, to provide efficient optimization through our REST API to our customers who are trying to, I'll simply say, optimize all sorts of things. And some of those things are machine learning models, in particular, maybe optimize the validation accuracy of a machine learning model. Could also be used to minimize the training error in a back test for a financial model. And in fact, over the years, many of SigOpt's customers turned out to be financial customers, which was an interesting twist, and I got a chance over the years to learn a lot from that. We also had, and much of the work that I'm most proud of, is the enablement of optimal design for physical products, for actual things that are being manufactured. And even before I started there, this was happening. There was an example, and the name escapes me right now. George Bonacci, I remember, was the scientist. I can't remember the name of the company. He was making shaving cream, and he was trying to design shaving cream to be both very robust and smell nice, but also then not fall apart. Because if you mix it the wrong way, the emulsion is wrong, then it just turns into water or something like that. And in reality, what was exciting was he was able to use a tool like SigOpt to come up with a really effective formulation of his shaving cream. So that topic, whether you call it formulations engineering, whether you call it computational chemistry, whether you call it materials science, the application of a tool like SigOpt for optimal design in each of these settings has been very exciting. Some of the work that we've been able to do over the years has been with materials scientists and making sure that they know, hey, a tool like SigOpt, even though we think of it as maybe a hyperparameter optimization tool, we certainly market it like that. It really has broad usage, and I've been so lucky to work at a company that was willing to explore that, to not just say, hey, we're going to do hyperparameter optimization only. We're only going to talk to ML people. We don't want to hear about anything else. I've been very fortunate to have some really visionary founders as part of the company who said, no, you know what? If there's an opportunity, let's go after it. Let's do some good work. We've been able to do that and develop new features, including the article that you mentioned, which branches beyond, I think, what's often discussed in any sort of ML training or HPO, and is most useful in these physical situations, in these maybe expensive, either computational simulations or even physical manufacturing. One of the best experiences of my life was being able to actually touch something that was manufactured as a result of a design that we suggested to the folks. And I'm just very fortunate to be a part of that.
Yeah, that's super cool. And the paper that we were referencing, it essentially touched on Pareto frontiers. And these are sort of the optimization frontiers of multi-constraint or multi-objective optimizations. So for instance, if you want to optimize price of X while minimizing the amount of materials you are using to create X. Well, those are two objectives that you're looking to optimize, and sort of the boundary is the Pareto frontier. And we were doing a lot of that work with A/B testing, where let's say we want to optimize revenue while increasing engagement, if they're sort of inversely related. So that it was a really, really interesting paper and had a lot of novel sort of concepts that I really enjoyed. So do you typically think about optimizations in terms of a Pareto frontier or just sort of a search? Can you sort of explain how you go about thinking about optimizations in general?
Absolutely. And I want to start by clarifying, especially for an ML audience. When I talk about optimization here, I am not talking about gradient descent. Gradient descent is a very important tool for optimization, but that's not what I'm talking about here. Really, what I'm talking about is circumstances where, in general, you don't have gradient information. Almost certainly you don't have gradient information. You also don't have any specific structure associated with the problem. The domain that you're looking at to optimize is, let's say, between, I don't know, 4 and 50 dimensional. So not in the order of the billions that, of course, we're talking about when we do gradient descent maybe nowadays, but also not 1 or 2 dimensional. There's an old phrase I think Warren Powell always used to say, everybody's a hero in 1 dimension. So we're not talking about sort of the most simple situations here. We're also not talking about the situations where you'd use either linear programming or gradient descent. And also I want to say that the domains we're often talking about optimizing over usually have some sort of certainly categorical element to them. So we're not optimizing over a continuous domain. One of the parameters might be red, green, blue. One of the parameters might be using the hyperbolic tangent or the ReLU activation function. So I think that it's important to mention that, because a lot of times when people hear optimization, they think atom. And that's reasonable, but when I'm talking about it here, really what I'm talking about is being efficient, being extremely sample efficient. You're only going to get a small number of, mathematically speaking, function evaluations, or from an ML perspective, we could say trainings. From a financial perspective, we'll talk about back testing. From a physical products perspective, we talk about actually building the thing, actually using the material and building the thing. And that is slow. It's slow and it's expensive. And perhaps, especially from a slow perspective, you may only have a week, 2 weeks to build something out. If it's going to take you 3 hours each time you want to test it, you need to come up with an answer pretty quickly. And that's what we focus on. And in particular, while it is obviously logical to talk about this in the context of optimization, because we are trying to make something go up or down, that's definitely trying to happen. I am trying to balance the use of the term optimization against the topic of mathematical optimization. And in particular, in the article that you're referencing, one of the key elements here is this idea that optimization itself is a very poor formulation for things that are happening in the real world. Mathematically speaking, it's a logical formulation. I have something, I want to see the best performance, find the point that gives me the best performance. That's not surprising, it's very logical. The issue is, and the thing the paper really tries to delve into, is the idea that what you are studying when you conduct this numerical optimization is not actually what you're interested in optimizing. Let's take a financial model, for instance. When I study historical data and I try and build a model that's going to perform well on historical data, that's all well and good. I found something that's going to perform well in the past, but that's not really what I'm trying to optimize. What I'm really trying to optimize is performance in the future. I'm trying to optimize how something is going to perform next week. Now, how it performed last week is a reasonable proxy for how it's going to perform next week, but it's not the same. They're not the same. And so when you go and run a mathematical optimization strategy and say, I'm trying to find the one point that is the answer, even if it is, even if you miraculously happen to find the one point in a, at least partially continuous domain that actually is the answer, it's the answer for last week, it's not the answer for next week. So you exhausting a huge amount of energy to find the answer to the wrong problem is not what I think of as a worthwhile investment. And really what the crux of the paper is trying to focus on is this idea that, hey, what you are trying to do is not what you can do. What you can do is just pointing you in the right direction. So don't bother trying to zero in on the 1 point or on the Pareto frontier. Admittedly, the Pareto frontier is more than 1 point, but it's still brittle. Being on or off the Pareto frontier you're talking the tiniest fraction of things. A point is on or off based on 0.00001 of one of its objectives, one of its metrics, one of its outputs. That's not appropriate. That's not the real world. And I don't think people even use it that way. A lot of times when people get the Pareto frontier, they don't just want everything that's on the frontier, even things that are close to the frontier they're interested in. Why is that? They're interested in it for a couple of reasons. Number one, noise. The measurements that you're taking when you do your training, even if the training itself is deterministic, the data you observed to conduct the training was done in a noisy condition. So the objective you're studying is noisy. And then number two, people know intuitively that what they're doing isn't what's going to play in the future. So people want data that isn't even the frontier. People want data that isn't even the answer because it helps them understand what's going on. And that was the crux of the papers. We wanted to embrace that. We wanted to say, hey, let's find not a point, but a region. Instead of converting this, let's say, 8-dimensional search place that we're playing in, and saying, I want to find a 0-dimensional point inside this 8-dimensional space, I want to find an 8-dimensional region inside this 8-dimensional space. And then there's a lot of follow-ups as to how to make that happen practically, what the implications are for multiple objectives, and whether this sort of or how to use the result of this, whether this is actually the answer then or what's the next step. I'm happy to dive into each of those, but that was the motivation of the paper. And where this came from was, again, the material science work, collaboration with the University of Pittsburgh. Dr. Paul Liu at the Laboratory for Advanced Materials in Pittsburgh is working on glass manufacturing. And when you're trying to build a piece of glass like this, in particular, you can see a reflection here. Oftentimes you actually don't want reflection in glass. Suppose you're looking at your cellular telephone. If your cellular telephone is reflecting light, that means you can't see what's behind the glass, which is really what you're trying to look at. Also, you don't want glass that leaves fingerprints. You want it somehow to be both hydrophobic, oleophobic, fatphobic, not to have oil stick to it. Omniphobic. You don't want anything to stick to the glass. That's important for phones. That's important for solar panels. That's important for all sorts of things. How do you design that? Well, that's a complicated question because you can build these numerical simulations to estimate how something's actually going to occur. But again, they're wrong. They're just models. They're estimates of what's going to happen. So you going out and trying to find the answer on the wrong problem isn't as helpful as you might like it to be. There are other reasons that the constraint-active search methodology, which is this methodology that I'm talking about here, there are other reasons why it's useful, in particular for involving expert opinion. But really the key crux of things is the idea of converting the problem from saying, I want to find this single point to I want to find some region, some answer, and I want to find an interesting selection of points from that region.
Yeah, it's really interesting that you bring up that aspect of, hey, this isn't just for AI folks or data scientists for applied ML, but also for the physical space. Because I'm one of the, I don't know how many people are out there with my background, but came from the physical space where we were applying some of these theories. Definitely not the sophistication that your company approaches this with, but that foundational idea of design of experiments where you take experts and say, all right, what are our hypotheses to, this is critically important in R&D when you're thinking about, we're going to create a new product that does something that none of our products currently do. Where do we even get started? And you can brute force it. And this also applies to ML, which I found years later when I moved into machine learning. I was like, oh, this is the same as like a random search when you're just guessing at stuff and saying, I hope for the best. Or you can approach the problem with, well, what are our boundary constraints of what we can do? Like, what are the tools? What are they physically capable of doing? How high can we set the temperature? How low can we set the temperature? How high and low the pressures are, the gas flow rates and stuff. And nobody does that in R&D because you're either going to break your tool or you're just going to make garbage. And everybody knows that. The experts know, like, no, we're not going to run it at minimum temperature. It's not going to work. So, and that's grid search from an ML perspective, when you're just saying, hey, generate all these different experiments. But when you're talking about that in the physical world, time is money. Gases cost money.
Yep.
Turning on the heater in a tool costs money. So we would do something similar to what you're talking about, which is informed hypothesis testing through design of experiments, saying, what do we think our ranges are? And people would come up with ideas and say, here's my theory on how we could do this. And then we would have a voting round in a room, sitting around a table. And,
awesome.
and everybody would say, you get 10 experiments to explore this space. Let's figure out what kind of works. And then we'll iterate on that. And then 3 days from now, after we reviewed everything, we're going to do 10 more. And that's what we were doing. We were constraining that n-dimensional space to an area where we say, okay,
Perfect.
This is where we need to move past the exploratory phase into, let's figure out how to make a product here.
Yep.
And if your tool does that, I am angry that it didn't exist 10 years ago.
You have perfectly nailed it. And that exact topic you talked about, you get the experts in the room and they vote on it. That is that expert opinion element that we were trying to support. And when you talk about optimization, the answer is whatever the highest point is, the point. When we talk about constraint active search, the goal was find a region. The region is, in this case, implicitly defined. Users give their statement of what they think is an acceptable level of performance. We try and find a bunch of points inside that region. The goal of finding that selection of points is exactly what you talked about. Now we're going to give these to the experts. We're going to give these 5, 10, 15, 20, however many points we were able to find to the experts. They're going to pick the 3 or 4 that are actually going to go into manufacture, that are going to take 6 months to get manufactured. And I love to hear. I love to hear that is taking place right now, because we hear it from people. But I think and this is the difference between making something happen practically and then writing an article about it. Because I can say, I talk to people for whom this happens. But how often do you see an article say, 10 of us got in the room and thought about what we wanted to test, and then we picked this to test? Like, nobody writes an article about it. So when I tried to cite people and say, well, I promise this is happening, some of the reviewers were like, you sure people actually do? So I'm like, I promise people do this. And the reviewers, the ICML reviewers actually were surprisingly accommodating, surprisingly supportive on that front. And they're like, we love to hear it. Good. We just want to make sure that you're actually talking to real people and not just inventing a fake problem out there. So I really need to give some kudos to the reviewers, because it's easy, especially at an ML conference. It's easy to be like, oh, you're not doing computer vision. Nah, we don't need that. But the reviewers are very, very accommodating, very excited, very open-minded. I appreciated that.
I mean, I would argue with that statement a little bit, or strongly, actually.
Please.
With not your position, the general consensus position of like, oh, it's AI, it's ML, computation is cheap, we can just iterate through a bunch. Like, do we need things like this? And I would argue that, to your point that you made earlier about we're finding this one point, and that's what traditional cross-validation is. It's just saying, give me the lowest RMSE, give me the Bayes information criteria score that works the best. Well, if you tweak your parameters just a little bit, and all of a sudden it falls off the face of the earth because of some sort of split of the data that made that one iteration work really well, or maybe you're converging and optimizing at a point where it's not a linear relationship along that gradient. You're finding like a local minima, and you've optimized to that. Well, if the data changes just a little bit, the model just is garbage. So that's why whenever I talk to practitioners, and it's funny, I'm working on a project right now that uses something similar to SigOpt. It's just the open source, like HyperOpt and Optuna.
Yeah.
And if you're not using tools like that, which they do give you, that one result at the end.
Yep, absolutely.
But you can see the history, and you can consume the history and parse it and say, what's the population distribution around these values?
Very
How
true.
many are good around here? And I want to select that range for my parameters that I'm going to use in production. But so few people do that. So I think your paper is awesome, and I think more people should read it and talk about it, about how important this is.
I definitely also want to call out, you mentioned open source tools. HyperOpt, James Bergster, outstanding tool, not necessarily being updated still very actively. Right. But when that paper came out, I remember it hit, and I remember people being like, wow, I love it. And Optuna, I have good friends at Preferred Networks working on that, Shotaro Sano, Masahiro Nomura. And Those guys are doing really fantastic work. In fact, I think Hideaki Imura will be speaking at our session at the upcoming International Conference on Industrial and Applied Mathematics in October in Tokyo, where we're going to be bringing together some of these experts in sample efficient optimization, thinking about things, talking about things. So I definitely want to give a shout out to them for doing outstanding work. Also to the great people at Meta, Meta, who are doing the Blowtorch project, which is also one of these tools. And I'll throw in a minor plug for ourselves. We also will be open sourcing SigOpt in a few months here, subject that we need to get through the legal stuff, the licensing, and so on. But this is something that we've been pushing for since we joined Intel. One of Intel's things is open source. Everything open source, put it out, get it out there. Let's make sure that we can build a community around it. We're very proud as a byproduct of the acquisition to be able to contribute to that Intel software ecosystem, and look for that ideally by ICML this year, which will be right here in Honolulu. So I'm also looking forward to that.
Yeah, you and I need to talk after this podcast is over about that. That's fantastic news, and
Very good.
It is great when you work for a company that's really big, that also really believes in open sourcing tools. Agreed. And we've had a number of developer groups that have come on in, heads of engineering at these companies, that people just want to enable everybody to not have to sign contracts and stuff. It definitely supported tools are generally better, particularly for enterprise uses. You want somebody who's maintaining that, and you're paying to maintain that.
Yep.
And everybody's got to eat. But there's also this thing to say about giving stuff away for free that allows advanced users to not just use it, but contribute to it.
Yes.
And making everything better. That's what we live and breathe by at Databricks, is that whole collaboration. And there's a lot of collaboration that happens, which hopefully you'll see, very shortly when you go into that open source, where other open source contributors for other packages start talking to one another, on the sideline and saying, hey, we'd like to integrate with you, or hey, let's do some PRs on each other's projects and let's make them both better.
Absolutely. So absolutely. We're definitely looking forward to that. It's in some ways it's maybe overdue, and we're glad to see it happen. We definitely want to see people take advantage of it who haven't been able to thus far, for one reason or another. And in particular, make sure that we're actually integrating into as much as we can, and being a part of the community, exactly like you said.
Yeah, I mean, I've heard testimonials. I've worked when I was in the field at Databricks working with customers. I've seen your product being used at a dozen different major companies, and everybody's just had nothing but the best to say about it. And that's the sort of the constant thing that who comes in contact with is like, man, I hope they open source this someday, because this thing's awesome. So yeah, everybody loves it. So it's
glad to hear it.
Great job to you and your team at building a fantastic product.
I will pass that along. I'll pass that along. And also I'll give thanks to everybody who's part of the team, and especially everybody who's still with us today working on the open sourcing project. Really outstanding work, folks. Thank you very much.
Now, what are sort of the benefits of using SigOpt versus a traditional open source tool like HyperOpt or Optuna?
The main benefit that I think of when using the hosted system is we're managing the computation for you. And in particular, some of these computations that we're doing are expensive, which is logical. We talked earlier about this idea of sample efficiency. When you are taking hours or days to do a neural network training, or to build some sort of financial model, or run some Navier-Stokes solution on some nasty cavity problem or something, every test matters. So we want to invest our time to make sure that you can get the best result as possible within the limited amount of time that you're going to be running your test, your optimization, your search. And by hiding that from the users. They only feel the pain of the 100 millisecond, we hope, API call that they're doing. And if you are running one of these other tools, you'll have to incur that burden somewhere. And so that's one key benefit to the system. I also think we manage parallelism quite effectively, both from a mathematical standpoint. I'm very proud of the work we've done there behind the scenes, but also from a infrastructure standpoint. I think we manage parallelism quite well. So if instead of running one training on one machine, you want to run 10 trainings on 10 machines or whatever your budget allows, you can do that. And the sort of reward or dividend per run decreases slightly as a result of parallelism, because at the end of the day, mathematically, we have to make more decisions with less data. If I have 0 pieces of data, I need to tell you what to do on the 10th thing. That's going to be slightly less good than if I had 9 pieces of data and I tell you what to do on the 10th thing. And of course, that's how SigOpt and these other tools are all powered, is this intelligent decision-making process. And if you talk to people on one branch of things, they might use this phrase sequential decision-making. I think nowadays that sort of is very specifically maybe for RL, but even RL, a lot of RL people, I think, can think about what they're doing, and some RL people may even be using this Bayesian optimization methodology to push things forward. I'll comment that another thing that I think SigOpt does quite well is bounces back and forth between different strategies internally. I mentioned Bayesian optimization, and indeed, Bayesian optimization leveraging Gaussian processes, which was my own research topic back when I was a student. This is extremely powerful, and I'm happy to talk about why I think it's extremely powerful, but let's just say it's extremely powerful. But it doesn't mean it's perfect for every situation. If you're running something at 50, 60, 70 parallelism, I'm personally will say I'm dubious that Gaussian process tools are the right thing. I'm happy to be told otherwise. I'm happy to have discussions. There's some really outstanding, brilliant researchers out there with whom we have fantastic discussions all the time about this. But even me, as big a GP fanatic as exists, thinks that other tools are useful in the mix. And I think SigOpt does a fantastic job bouncing between different options and making sure that the right tool is being used for the right set of circumstances. In addition to that, the new methodology, constraint-active search, I believe it's the right tool for not just, we talked about sort of single objective problems, we're really pushing these multi-objective problems. When you're talking standard multi-objective or multi-criteria, multi-metric problems, you're talking about the solution being the Pareto frontier. That is the standard definition of the solution. It doesn't mean it's not a useful piece of information, but like I said, it's brittle. There's something dissatisfying about it. Not from a mathematical standpoint, but from a practical standpoint. It feels like you're leaving data. It feels like you're leaving answers on the table. And in particular, what I find frustrating about the way a lot of tools that search for the proto frontier are trying to do so is they really define success as just, I want to spend all my energy clarifying every point that's on the proto frontier, and maybe missing a big chunk of the region that's full of useful, viable outcomes for eventual production, or for presenting in front of experts and saying, hey, you have thoughts in your mind about how this is actually going to work later on. What can we do with this information? SigOpt has not just this implemented in place, but in particular, this running right now for scaling up to 6 objectives. We could go higher, but we've only tested it well for 6, in my opinion. And I'm really excited about that, because when you talk about Pareto frontier, in 2 metrics, I should say 2 objectives, okay, Pareto frontier is this nice little line, fine. I can live with it, I can look at it, I can feel it, I'm okay with that. You get to 3 objectives, and you're talking a surface. I can still visualize it, so I'm happy about the fact that I can visualize it, but how many points do you really need in order to approximate a surface kind of well? Hundreds, thousands, I don't know, a lot. So if you're talking, you need hundreds of points on the frontier, how many total runs do you need to do to get to 100 winners or 1,000 wins? talking hundreds of thousands before you know it. And that's just for 3 objects. Suppose you're trying to go to 4, 5, 6 objects. It doesn't scale. That is the curse of dimensionality. When people talk curse of dimensionality, that is what they mean, is that the pain of trying to study things in increasingly many dimensions just renders standard attempts to do so as infeasible. In contrast, the nice thing about this constraint-active search methodology that we have available in SigOpt today is that you can run this in higher numbers of metrics, and because it converts the problem from a straight optimization problem into a sort of yes-no statement. Yes, this is a viable point. No, this is not a viable point. The complexity of adding additional metrics, the computational cost on our end increases, but the conceptual complexity doesn't increase at all. You're simply adding another metric. You're simply maybe whittling down the region into something smaller and smaller, but it's not actually changing the concept of the complexity of the solution the way that the complexity of the proto frontier increases significantly as you increase the number of metrics. So that's another reason why I'm really excited about it, why it's really useful.
It's interesting how you brought up the parallelization and computational burden of these. Like at Databricks, we have distributed HyperOpt, which
good.
It's pseudo-distributed. So we didn't take the HyperOpt package and library and say, hey, we built a mathematical formula that you can distribute to n number of cores and it'll just work, because that's impossible. You can't take that tree of parse and estimators and have it dynamically update in real time and modify things that are already running. So you're constrained by, like, you can run more tests at the same time. You want to run 1,000 at a time? Go nuts. Yeah. It's not going to improve it at all.
It might not.
It'll take a random search space to get that initial feed. Yeah. And that's random throughout the space. Yeah. It'll spam that out to all these executors on Spark. But then when it's iterating on the data that's been shuffled around into all of these partitions, it's still using the standard HyperOpt library. Gotcha. So we do a barrier execution mode where we'll do like, hey, 10 iterations, see how good you get, send the data back to the driver and say, who's best? Or what's the range of best values that we've gotten from all these different tests?
I like it.
Now send another iteration out and do that. And improvements to the way that works. That's what really excited me about what you said about what SigOpt is working on, is thinking through, like, how can we do this a little bit better and not be constrained by that whole like iterative distributed process and make it so that somebody could get not just that right answer that everybody's focusing on, but hey, what's that gradient within this dimension that we should be thinking about, so that when we want to do something like retraining, and I've heard from a lot of customers, and I've had to implement it myself in the past, where we have automated retraining, like active retraining systems. Oh, I'm drifting down and we're losing money from this algorithm. We need to kick off training again. Well, you don't want to have your training code be the same code that you use during initial development of saying, here's my massive search space that I'm going to be looking through. You want to constrain that down to say,
yes, you do.
Over the last 5 runs that we've done retraining, what were the best parameters that we had? And what's the distance between those spaces? Add 10% on continuous on those boundaries. And if it's categorical, if it's really like one thing is just dominating everything else, then okay, let's use that and fix that. We don't need to search over that. But being able to do that and to have that result from your optimization algorithm to say, this is the space we should be in, is so incredibly powerful to make that process of active retraining or passive retraining so much cheaper, because you don't have to do 1,000 iterations. You can say, retraining, just do 20. We already know the space we're supposed to be in. I just want to tweak it and get the best for this one particular run.
And I couldn't agree more with what you said. And I'm going to take 1 second here to confirm that I remember the title. But we just actually put out a paper to the TMLR, the Transactions on Machine Learning Research, which is part of the JMLR's new initiative to publish stuff they feel like doesn't fit somewhere else. And in particular, this paper was a perfect example of that. It is a discussion of exactly as you're talking about how constraint-active search provides a strategy for, we maybe use the word hot swapping models that are in production. So effectively, you could have your constraint-active search leave you with 4, 5, 6 different winners, and then you can put all of them effectively in production in some sort of a multi-armed bandit situation. And that gives you the ability to, exactly as you're talking about, maybe do a passive retrain or an alternate model that's already ready to go and has been, as you've seen, performing better in live data as opposed to just the data that you've observed in the past. And the article is called, there it is, Bridging Offline and Online Experimentation. And that was one of the follow-ups to the original ICML paper. And that was a collaboration with Junpei Komayama at NYU Business School, Stern Business School. And I love the idea. I love being able to tackle these practical problems that we're talking about here. In some ways, this isn't even, that's the key, is that mathematically, it's like, oh, well, just retrain it, just do it better, get the answer, get the best point. Why would you do anything else? But then from a practical perspective, no, real problems exist, real limitations exist. It is a fair question to ask, and this is a legitimate question to ask, whether ML conference, ML journals are the right forum to engage with this on. I think that's a fair question to ask. In some ways, it's a balance of how much theory is there versus how much is this deployed systems. KDD has that specific deployed systems track that I really like, where people just talk about things. They have the discussion, they build up the community around practical circumstances. I think that having that and having journals like TMLR, which are used to talk about things that maybe don't fit perfectly in a theoretical context, but are still of relevance to the community. I think the community, it's growing, it's adapting, it's changing. It's an interesting question. Where do things belong? How do we talk about them? How do we build the community, grow the community in a way which is engaging, but also focused? I think it's complicated. And I think that it really takes everyone in the community working together, being friendly with each other, that's nice, open-minded, and then also it takes a vision. And that's one thing that, I'll be honest, I worry slightly about on the ML publications front, is that right now I don't see someone, there is no boss of ML, but I don't see the heads of the conferences or the heads of the proceedings necessarily having a specific vision for how these questions are going to pop up. How are we going to deal with the practical elements versus other elements? Exactly as you talked about before, how are we going to deal with, they're trying, I give them 100% their credit, for how to deal with this question of very brittle models, or these, okay, you tune the whole thing, or you found some set of hyperparameters, the thing works perfectly on that with that split of data that you have, everything is great, put the paper out, anybody tries to reproduce it, it just sort of collapses, or something like that. Or even these other situations, this is complicated, but it cost you $50 million or whatever in AWS credits to train this thing, and then you publish it. I want you to put it out there. I want you, that was a huge amount of money, a huge investment. I'm glad you're putting the information out there. But then it's this complicated thing when you're putting out research that nobody could even attempt to reproduce in any viable set of circumstances. To say nothing of the fact that almost immediately, as soon as you put some of these things out, they're out of date. I've had reviewers say to me, why didn't you cite this archive paper? I have my own personal beef with the archive. Why didn't you cite this archive paper that was put out after you submitted this paper? I'm like, well, I don't know what to say about that. And so we as a community, but I think it needs to come from the top down, because the community is growing so fast, and you've got so many people with so many different backgrounds in there that somehow you need authorities on the topic to say, hey, reviewers, be a little more open-minded, be a little more not dependent on just spamming archive for, hey, what's the latest thing? I'm going to compare it against this. Not complaining when there aren't 95 different benchmarks that you compare something to. And also, frankly, it's my own personal opinion, not letting papers get published just because they compared against 95 different benchmarks. Because if they didn't put any concept, any hypothesis, any desired outcome into their thing, it's like, well, then they just tested a bunch of things and said what they did. And it's like, I don't know. I'm not sure that's what we should be publishing. So, whether it's my controversial take of the day.
I happen to agree with you on pretty much all those points. When you work with companies that, like as a vendor, which you're familiar with, you work with a company, you know, within a half an hour of talking to a team when they're talking about a project of like, okay, they thought this through. They know what they're looking for. They're going to use our tool to solve a real use case. It's either going to make them more money, make them lose less money, do something interesting in the real world. And then you also know, after talking to enough people and enough teams, within probably 5 minutes, whether or not they know what they're talking about at all, and whether this is just a pipe dream. Somebody read a blog post, somebody read a paper, and they're like, we need to reproduce exactly what's in this. So sometimes those companies have an obscene amount of just rainy day funds.
Yeah.
Let's call it that. And they're willing to pay a company of experts to come in and build something. And I've had that handed to me about a half a dozen times in the last 4 years, where you show up in a room full of people and they're on a massive TV screen that's, the size of my car at the head of the whiteboard of the table, and you're looking at it and you're like, all right, there's a white paper on the screen. I'm like, okay, let's read through, like, what do you want to do? You're just reading through it and you're like, there's like a Python package that does exactly what you're looking for, and it'll probably run 10,000 times faster than what we're talking about here. And it's free. You just have to pip install it.
Yeah.
And they just straight up say, we're not interested. We want you to help us implement this paper. And I'm like looking through pages of mathematical formula. I'm like, okay, let's get to work.
Let's talk.
One of the ones we did was somebody was like, we want to do matrix, basically dot product matrix inversion operations on a distributed matrix on Spark.
Right.
Like, we want that algorithm. Like, but why?
Yeah.
They're like, we just need it. So it was a paper. The paper was really well written, super fascinating, had 3 citations after a year being published.
Yeah.
And it was just so far beyond the scope of what anybody would really need to do. But they paid us to implement it, and we implemented it.
Very nice.
But then we used an algorithm that's in Spark ML that's free for them to use, and it performed better. I was like, this is why we didn't, like, this is why this algorithm doesn't exist in Spark, because it's so bespoke.
Yeah.
And it's cool that it worked for that paper, but it doesn't really work in the real world.
Yeah. I'm when I hear about that in particular, I grew up in numerical linear algebra, so I'm definitely a big fan of the matrix computations. Charlie Van Loon was my advisor, and I so rarely get to talk about that. In particular, if I'm not mistaken, the Google people, the DeepMind people, put out, I don't remember who, put out an article talking about how they did a search and found better ways to multiply matrices together of various sizes, which of course I found extremely exciting, very fun. I don't exactly what you're talking about. I don't know exactly how practical it's going to be, though they claimed they were able to see some nice pickups in some of their TensorFlow stuff, which is really cool. But yeah, exactly to your point, sometimes what gets done in a research setting can be important, and it's important that you get the idea out there so that people know about it. But whether it actually gets traction can be subject to a lot of practical considerations that aren't, and in my opinion, shouldn't be a question of whether an article gets published. Certainly not a question of whether an article gets published in SIAM matrix analysis or whatever. Like that's not the forum for practical concerns. The forum is exactly as you're talking about. Hey, when you go in to answer questions for somebody, is this viable or not? Trust me, I'm the expert. I know you shouldn't do this, but yeah, if they're paying, it is what it is.
Yeah, and that's a great segue to one more topic that I wanted to cover in the very limited time that we have. So, Mike, you started off with a background in mathematics, and then you got your PhD in philosophy, worked in some national labs, and then eventually became head of engineering at SigOpt. And so you've
National Lab.
yeah, let's go. He held up his mug for those of you listening.
Sorry,
in.
yes, sorry. Yes.
And I was wondering how you think about developing a team culture that promotes innovation. Because now that you're ahead of a team, it falls a lot on your shoulders. So how do you think about that?
Oh, yes. Excellent question. Extremely important topic, and something that I think companies really, really, really need to be thinking about right now. Universities also do. And in particular, I think professors who are building up research groups should be asking themselves, how do you build an effective group, an effective culture? I believe, I think it needs to come from both sides. I think the boss needs to be looking for a variety of different folks. And in particular, I keep calling out SIAM. SIAM, for those of you who don't know, Society for Industrial and Applied Mathematics. That was where I grew up. And when I grew up there, I felt like I was doing good work. I still think I did some good work there. There's some good work getting published at those conferences. But I would argue SIAM people are very underrepresented in the tech industry right now. And I'm going to argue a hefty dose of that falls on math departments. Not encouraging people to get out of the shell, not encouraging people to go take internships. I remember offering an internship to somebody over the fall semester, and his advisor was like, nah, I think it's more important than kids in class. And look, as somebody who used to teach, I used to teach University of Colorado, I believe class is important. Class is very important. But it's a unique opportunity to be able to spend a chunk of time in San Francisco, not just doing good work, but frankly also doing research. We wanted to publish an article together, and it got spiked. And I was like, wow. So some of this comes from the supply side. People need to be available. They need to be excited about it. They need to see it as an opportunity. And right now I'm speaking specifically to PhD candidates. Do not assume you are going to get the faculty position. It may happen. I hope you do if that's what you want. I 100% hope you do. But do not assume you will. Check out your options. On the other hand, I think it is important that team leaders who are recruiting, who have the ability to do personal recruiting. I've been very fortunate, both startup and since I've been at Intel, to be able to go out and recruit my own people, to be able to go out to job fairs myself, pull people into the mix, say, hey, let's talk. I want you. Let's make this happen. I've been very fortunate to be able to do that. I think at some companies, you get whatever HR gives you. So maybe there's a gap there that needs to be figured out. I'd love to see more companies reaching out beyond just recruiting at ICML and NeurIPS and ICLR. I think it takes energy, it takes effort though, because you read some of these resumes, these CVs. Can you parse them? If somebody says, "Hey, I did this sweet project on numerical PDEs, solving boundary value problems in MATLAB," does that translate to your ability to do stuff in a tech company? Frankly, the answer is probably no. Like, very little of that immediately translates. I really hate to say that. As somebody who spent plenty of my graduate studies doing exactly that, breaks my heart to say that. But honestly, no. When you work on a project all by yourself, without any, collaboration, with very little project oversight until sort of the end, and then you check in with the boss, you're like, is this okay or not? It's not representative of that. When you don't use version control, it's not representative of how teams actually function, how iterations happen when there's no code reviews. So I am going to put a burden on industry in general to say, hey, we need to make sure to send these things out. I've gone to universities and I've given talks where I explain to folks, I'm like, hey, if you want kids in your department to start being able to go to industry, this is the stuff you need to do. And these aren't complicated things. These are all things that you're doing anyways. You just could be doing them a little bit different, and your kids would be ready to go. And then when they talk to employers, they could actually say the words that they need to say in order to get hired, and actually talk about, yeah, we did GitHub. Yeah, we did pull requests. We did code review. Yeah, I have these example projects or key projects that define my PhD. You spent years doing it. You put none of the code out there. No README, no blog content for any of this. It's all just piled up in this 400-page tome that's probably just sitting on your mother's shelf, which is good. My mother has mine on her shelf. But the point is it's like that's not how you're getting out there. It's not how you're going to be a part of a cool team. So I think some of it's from the supply side and some of it is the industry side. If the industry wants to get these incredibly talented, outstanding statisticians and mathematicians and people from operations research, for the people who are part of the informs community also, all those folks should be pulling good jobs out there. They're all really smart. They're all really capable. I think it comes from both sides, and I'd like to see more of that from everybody. And I need to do that too. I need to keep being out there and making that happen. And if that happens, I think we're going to have a better workforce, a workforce that has more solid skills, and we're going to have more students being able to join and make big contributions. So there's my plug for math education, but also getting out of your bubble and making things happen.
Nice.
Yeah, it's amazing what we see in the difference between a first-year intern. I mean, somebody that's doing a CS program. We get an intern who's coming from Berkeley or Stanford. They've already done internships in their undergrad, working for some SF-based company, and they already know the ropes there. But if you get a PhD who's coming from math or physics that maybe never did CS work in the past, if you see them, 4 semesters later, the next year that they're doing something and they're like, all right, I'm working on, finishing up my defense and getting all this stuff ready to go through final review. And I just wanted to take, 6 months and work at a startup and, learn some more. When you see them again after that period, how much they've retained and how much they don't need any real supervision. You just give them a project that's generally the actual cool work that everybody wants to do, but we don't have time to do. The intern has time to do it. So you give them this amazing project and like, hey, can you do this in 4 months? And the success rate that I see on implementations is like over 95%. It's insane how great these people are. But they would not be able to do that if they didn't have that foundation of how do I do a peer review? Why do I need to do a peer review? And I think some academic institutions in postdoc and in doctoral research, it's like an isolating sort of environment. You're not getting that
very much so
peer feedback.
That's
what I thought that Stanford and Berkeley did something really great with, AMP Lab and Rise Lab at Berkeley, where they said, everybody sits in a room together and you're going to work together and you're going to ask each other questions and you're going to debate and it's going to be, and what's come out of that? Apache Spark,
really Ray, amazing stuff,
Ray too, scale now. These amazing projects that have built into they've rebuilt entire industries with what's come out of that collaboration within that lab and with them working with industry. So I cannot endorse your statement any stronger than you already did.
Very, very good to hear. I like to hear that. And I think there's an opportunity. It's just going to take a little open mind, a little bit of energy and change on both sides, and big stuff can happen. Absolutely.
Amazing. Well, I will wrap and then we can kick it over to Mike to see if there's any ways that people can get in contact. So,
by all means, please.
Cool. So just to sort of recap what SigOpt does, they focus on unstructured optimizations, whether it be financial models, machine learning, or shaving cream. And some core benefits of the tooling is computational management. And then they just have really smart algorithms that bounce between, let's say, Bayesian optimization or other methods that are very specialized for a given use case. And hopefully some of this will be open source in the next few months. I know I'm waiting. I have a project where I will implement it if it's out in time.
Very good.
And then one thing that really stuck with me is this sort of interesting reframe of optimization to think about acceptable regions instead of optimal points. When searching is expensive, this is a really effective reframe to improve your efficiency, essentially. And this is called constraint-active search. And then finally, on the innovation piece, bosses obviously need to look for good people, but also the people need to be interested and ready to join. And then finally, the underlying tenet from what I was hearing in this conversation is the teams just need to be productive. And often people don't take the time to invest in learning tools. You need to be able to be efficient with GitHub. If you're using Google Docs, you need to know about headers in Google Docs and be able to type English. That they're all very valuable skills. So with that, Mike, if people want to learn more, where can they find you?
Absolutely. First things first, our SigOpt emails are still alive for a little bit longer. So feel free to hit me up at McCourt@SigOpt.com. You can also probably better transition to Micheal.McCourt@Intel.com. I find me on LinkedIn, and we have a Twitter handle at SigOpt, to where you'll find some fun conference pictures and follow-ups to some of the exciting work you're seeing people who are using SigOpt today. We always try and hype our users' work because that's what we do it for.
Amazing. Well, until next time, it's been Michael Burke and my co-host,
Ben Wilson.
And have a good day, everyone.
Take it easy.
Take care.